Hi, OChem Stars. This is Mrs. Vanderlei bringing you more OChem Star video. And we have left off with section 3.7 where we have learned that alkenes react by addition. And addition always meant two products, and those two things just jumped on that double bond, okay? Well, that was something that we had symmetric, and this should be reagent, not reagents, all right, to unsymmetric alkenes. This is called Markovnikov's rule, okay? So what do I mean by symmetric and unsymmetric? I must have really had a bad day typing when I see things like this. I apologize. Bad and bad. But anyway, so what do I mean by that? Well, symmetric means evenly distributed. Well, if I draw a line down the middle here, isn't it the same on one side as on the other side? And the answer is, well, yes. Look at your reagents. Can I say that my reagents are the same on both sides? No, they're not, okay? So, and I can do the same thing with the alkenes. This is a perfectly symmetric alkene, and if I do this, no, it's not, because I have this methyl group hanging off. And does that make a difference? And the answer is yes, okay? So look what happens if a reagent and or an alkene. So if either, like this right here, either the reagent or the alkene is symmetric, then you only get one addition product, just like we did in 3.7 in the prior section, okay? So what happens, we're going to split the bromine up, and we're going, oops, Mrs. Vanderlei, we're going to do something like this. And there are my H's. All right, both bromines hop on the ethene, and we get 1,2-dibromoethane. Okay, so one product, right? One product. That's what we said earlier. Okay, now look what happens up here. There we go. I can actually do it this way. Ooh. Okay, so if both the reagent and, so you need both, and are unsymmetric, you get two possible products, okay? So let's call this, R is any carbon group, and then this is a hydrogen, okay? So what could I do? Well, when it breaks the bond, here's my R, I can put my X here and my Y there, and these are my hydrogens, okay? And or, let's break the bond again, here's my R, let's put my Y here and my X here. So I can flip-flop those two, all right, and get different products, okay? So these products are called regioisomers, okay? So the regions are different, but they have the same formulas, okay? However, that's like a but. If a reaction of this type gives only one of two possible regioisomers, then it's regiospecific. So if I could get two, but I only get one, it's regiospecific. And then if it gives mostly one product, then it's regioselective. So let's see what happens here. Now, when I had the acid catalyzed addition of water earlier, this is what section over here. Notice what's going on here. Water is not symmetrical, but the one I used here is symmetrical. So my ethane was symmetrical, so it made no difference. Well, guess what? Cyclohexene is symmetrical, so it really made no difference. Cyclopentene, whoopsies, is symmetric, so it made no difference. 2-butene is symmetric, it made no difference. Okay, but what about propene? Well, propene looks like this, right? If I put a line down here, doesn't this have two different sides to it? And if I use HOH, this is unsymmetric as well. So I have both the reagent, water, and my propene are both unsymmetric. So what could happen? All right, so in case number one, all right, I'll break the bond, and I'll put the H here, and the OH here. In case number two, I'll break the bond and put OH here and H here. Now let's name these real quick, all right? This would be 2-propanol, and this is 1-propanol. Why would I bother naming it? Here, I'll scooch it over. Because I'm showing you they're two different things. They're not isomers, they're two different things. To be more specific, they're regioisomers, okay? So what happens? With experiment, only one product is ever observed, okay? And it happens to be this one right here. This is my product that is observed, okay? So if only one product is observed ever, it is regio specific, okay? So let's see what else. What if I try propene and HCl? Okay, what happens? I can get two possible products. I can break the bond, put the H here and the Cl there. Or I can break the bond and put chlorine here and H here. Well, guess what? This is the one that you make. So again, it is regio specific. What about the next one? 2-methylpropene, ready? Plus water. Okay, so watch what happens. The first one, I can break the bond, and I can put the H here and the OH here. And in the second case, I can break the bond. This is a carbon, sorry, and put the OH here and the H here. Well, guess what? This is the one that is observed. Let's do one more. Cyclopentene. So this is one, actually this should be a 1-methyl, fix that for me. And then here we go. So once again, I'm going to break the bond, okay? And this is my carbon. I can put the H here and the I here, or, oops, I was trying to make cyclohexane. Here's my carbon, I can put the I here and the H here. Well, you know what happens? This is the one that is created. So these are all regiospecifics. So, oh, wait a minute, you're going to say, Mrs. Vito, I can't see that. You're right. So what is similar about each reagent? They are unsymmetric. Okay? I can draw a line down everything, and you will see that they're not the same on both sides. Okay? So how do you determine which products are or are not observed? So a good Russian, Vladimir Markovnikov, observed over 100 years ago through experimentation that when an unsymmetric reagent adds to an unsymmetric alkene, all right, the hydrogen part of the reagent bonds to the carbon of the double bond that has the most number of hydrogen atoms attached. All right, so this isn't going to work if we had bromine Br2 or chlorine Cl2. This would work with water or acids. Okay, so I'm going to write this down. Works with water, because there's a hydrogen, and acids. Why? Because there's an H and I'll put an X there. So if there is a hydrogen in the reagent, then Markovnikov's rule works. So what does it say? The hydrogen part of the reagent, so either the HOH, this part, or this part, bonds to the carbon of the double bond that has the most number of hydrogen atoms already attached to it. So I like to say this. The H's hang out with their friends. They're like BFF groups, all right? Hydrogens like hydrogens. So where there's more hydrogens at the party, the hydrogens are going to go there, okay? So let's look at this. 1-butene, okay, plus HCl. It says use Markovnikov's rule to predict which regioisomer predominates in each, all right? So this is where you need to count, all right? You ready to count? So count what? Count your H's. So how many H's are off of this one? I have one H and one H. And how many H's are on this one? Only one H. So where does this H end up? It ends up with a hydrogen that has more. So it's going to end up with this one. So this H is here, and here's the other two H's. And then the chlorine will go here. Okay? That one is the only one that will actually be produced. So let's try the next one, 2-methyl-2-butene. Again, what's the plan here? How many H's are on this carbon? None. It already has 4 bonds. How many H's are on this carbon? 1. Where will this hydrogen now go? It will go where the most number of H's already are. So when it makes the product, it's going to break the bond, and that other H is going to end up here. So that H is going to be here because there's already another H here. And then the OH is going to end up over here. Okay? So you'd call this 2-methyl-2-butanol is your product, okay? So it says, what two products are possible from the addition of HCl to 2-pentene, all right? Okay, so here's my HCl. Now, what did Markovnikov do? He checked out your H's. So how many H's are on this carbon? Just 1. How many H's are on this carbon? Just 1. Is there a preference? Will this H prefer one carbon over the other? The answer is no. So it's probably going to be a 50-50 split. So my first choice, I broke the bond here. I'll put the H here and the chlorine there. And my second choice, I'll do the same thing again. Oops. 1, 2, 3, 4, Mrs. Vanderley. There we go. So I'll put the chlorine here and the H here. So here I have 3 chloropentane, and here I have 2 chloropentane. So would I expect the reaction to be regiospecific? No. You probably got a 50-50 mix between these two products, okay? And that's all there is to this video. We'll talk more about it later. Take care. Don't wait to be great. Bye-bye.